Great. I'm going to share my screen. You guys should be able to see. Great. This should be my screen you guys are seeing. I went ahead and did some of this stuff during office hours. I think it was yesterday. And then I also made a recording on Thursday that covered most of it. So all that we have left are thermodynamic and kinetic products, our anti-periplanar conformations, and then synthesis. This chart I erased. If we have time at the end, we can run through it again just to see if we can get the hang of it at the end. But this stuff should go by relatively quickly. But the first thing I want to go over is thermodynamic and kinetic control. In my experience, a lot of my cohorts didn't study this enough. And this is something that you should really focus on, but a really easy concept to grasp is kinetic products is always 1-2 products, always. Now, thermodynamic products are always the most stable one, but 99% of the time it's 1-4 addition. And it's perfectly okay, in my opinion, my experience, it's pretty much okay to just recognize thermodynamic. All right, 1-4 addition, and then kinetic, no matter what, that's always 1-2 addition. So right here, this mechanism or this shorthand is kind of misleading because there are actually 2 other products that can come from this. The other 2 products that can come up is something that looks like this. CH2, Cl, and then something like this. Double bond here, CH2, I think a Cl as well right there. All right. And the reason why there are 4 products is, all right, we have 2 alkenes here and we have a hydrohalogenation. We know that hydrohalogenation, there's a carbocation intermediate and it just adds an H and a Cl over a double bond. There are 2 double bonds, and each of those 2 double bonds can do a 1-4 and 1-2 addition. And a very common question that you'll see, especially in the tests that I posted in the group chat, if you took a look at it, it's asking you which is the most reactive alkene, and we'll get to that later. But for now, let's just identify what we're dealing with. All right, so if our starting product is diene A, which looks like this, we're reacting with HCl. Well, let me do this in, like, I don't know, the pink, and let me do this in maybe red. So for the pink, let's do it if the alkene added to this, or the HCl added to this alkene. So nope. Something that you have to write when you're drawing mechanism. I don't think you'll have a specific mechanism page. I forgot if you do for test 3 or not. But something I saw in the test is you have to draw the arrows for the HCl as well. Something like that. That's a rate determining step. And if that was the case, then 1-2 addition. All right, well, secondary carbocation can be here, Cl. Oh, nope, that's supposed to be it. I was about to say, like, wait, what? Okay, H is right there, and then our alkene CH2 is right here. And there's a resonance structure right here before our Cl adds, is if this alkene just door-handed is over there, and we have CH2, and then just an sp2 one right there. Now, looking at this straight up, this is already our 1-2 addition, and this is our 1-4 addition. So we know that if we went with this alkene, this would be the kinetic, this would be the thermodynamic. And I'm just going to leave some side notes. It'll come later, but this is a secondary carbocation, there's a primary carbocation. Now, if we were to add HCl through this alkene right here, well, take that H, those electrons go to that chlorine, rate determining step, our alkene would look something like this. we have a carbocation right here, CH2, and then there's another H, it's just CH3. And then we have something right there. Then we have a resin structure that looks like this, where this alkene basically door hinges on that side right there. CH3. All right. And right here, this is our normal 1,2 addition. That's our kinetic product. This is our 1,4 addition. That's our thermodynamic product. And just to leave it on the side, this is tertiary, and this is secondary. And then obviously, our Cl just adds where, or our nucleophile just adds to wherever that positive charge here. And product 1 or 2, that adds through this bottom route, where Cl adds to that carbocation right there, Cl, CH3, and our alkene just stays put. And then we have the Cl adding right there, CH3, Cl, right? Drawing out those products is already pretty handy enough. It'll get you your points because you know what's happening, you know what's going on. But there might be a question, all right, which one's the thermodynamic, which one's the kinetic product? Well, we were able to identify that because we just label it as our 1,2 or our 1,4 addition. Secondly, what is the most reactive alkene? Well, we have 2 to choose from. We have the red alkene and we have the pink alkene. The most reactive one is the one that has the most substituted carbocations. This tertiary and secondary one right here. It's pretty obvious because if it's stabilized, it's a lot more reactive. That's a big concept, but hopefully that makes sense. So our most reactive one has our most stable carbocation intermediates. And I'm assuming you guys already took test 2. You guys know for this same deal, the Cl would add to the carbocation. So this product right here, product 3, our kinetic product for that one. And a product 4 over here would be over here. Does anyone have any questions on thermodynamic and kinetic products? There's not too much to explain other than just like being able to identify, right, this is 1,2, this is 1,4. I know I can just easily just slap a label on it.
Yeah, could you quickly explain the 1,2, 1,4 addition again?
Yeah. So in a nutshell, we have an alkene. This is symmetrical, so it doesn't really matter what side we add it to. Carbocation right here, H. Obviously, because for this alkene right here, secondary, primary, carbocation will form on the primary. If it's just a normal addition, for labeling it 1, 2, 3, 4, it adds to the 1 and 2 position. However, in another resonance structure, when this flips over, it's H and carbocation. And remember, wherever that carbocation is synonymous to where that Cl will add. We have 1, 2, 3, 4, 1, 4. 1,4 addition, 1,2 addition. So wherever there's a 1,4 addition, wherever it conjugates that, or that double bond conjugates, that's a thermodynamic product. And just straight up, just as it is, where it adds is our kinetic product. And if we apply that over here, all right, let's erase some of this noise. There we go. Nope. Okay. So if we're looking at the pink root, all right, if our alkene's right here, let's label it 1, 2, 3, 4. All right, 1 and 2, that's where it adds 1 and 2 for this one. This is our 1,2 addition, like I wrote before. If this alkene conjugates on that side, it's going to be our 1, 2, 3, and then our 4 is now where our carbocation is, because 1, 2, 3, 4, 1 and 4, 1 and 2. This is our 1,4 addition. Does that answer your question?
A little bit. It's more the second products underneath it that I'm a bit confused how you get that.
These ones?
Yeah, because it looks like on the first one, they both go on the third one, or the chlorine goes on the third one, if you're counting.
You have to start on the alkene you're adding on. You can't just label it from the nomenclature, because if we use this alkene right here, this becomes our first 1, 2. So the alkene you're adding on is always the 1, 2, because it's not absolute. We're just relatively trying to label what we're adding. It's kind of like the 1,3 diaxial string. It's not exactly 1,3 nomenclature wise, but it's just relative to each other. They're one carbon away from each other. The 2, which is the carbon in between, and then the 3. 1, 2, 3, 4. So right here, it adds 1, 2. That's our 1, 2 addition. 3, 4. However, this alkene splits over there, and basically 1, 2, 3, 4. The H added on the 1 still, and the 4 is where that carbocation is. So our 1, 4 addition is, or our 1, 2, 3, 4 application is always relative. 1, 2, 3, 4. It might, if you add to this alkene 1, 2, 3, 4, that's perfectly acceptable because it's relative. Even if you add an asymmetrical compound like this. If we added HCl to this one, nope. 1, 2, 3, 4. And you always go into the direction of the other alkene, because obviously the way this works, the 1, 4 addition, is that it conjugates over. So it kind of implies you need a neighboring alkene. So 1, 2, 3, 4 this way. If we add it, HCl. Let me close that up. Carbocation right here, H here. 1, 2, 3, 4. That's our 1, 2 addition. This alkene will conjugate over on this side, door hinge, and then this carbocation will now move over here. Okay, it would be H still, alkene over here. Now the carbocation is over here. There's still 1, 2, 3, 4. 1 addition, 4 addition. These are 1, 2. These are 1, 4. Kinetic, thermodynamic. Does that answer your question? Or clear some things up?
A little.
Okay.
I'm just gonna have to hope questions like this aren't worth a lot on the exam.
For this kind of question in the exam, it's more on just identifying or being able to draw the products, which you can kind of do just based on your knowledge of resin structures and hydrohalogenation. And then another portion is just identifying kinetic and thermodynamic product. We can probably try to take a crack at it on one of the tests I posted. Going into anti-periplanar stuff, this is pretty handy. I say one of the easiest concepts is just converting Newman into Fisher structures. All right, so a lot easier said than done. So this structure right here, we're supposed to fill in the blanks from this right here. However, it's really easy because if you look at it from this perspective, if your eyesight's right here and you're looking directly at it, bromine is right here at the bottom where it is. And then this side, let's say this is our wedge side. You know, CH3. Hopefully you guys see that, what I'm trying to talk about. For this front carbon right here, that's our front carbon we're looking at. And then H, because these structures that make like that little pronged triangle structure, that's our Newman projection. And obviously this is dashed. CH3 and H. Now looking on this side, right here in the back, well, that's this right here. The way we're looking at it from this perspective, CH3 is on the top. Let me erase this. This tert butyl group, CH3 is on the same plane as CH3. It's on this side. And then this H is also dashed. It's in the back. Do you guys see how I put that together? I know it's again, this is something really hard um online. I don't this is really a drawback because stereochemistry, it's spatial arrangement. And I'm telling you, it might sound really dumb, but it's kind of makes sense. It's a lot easier in person because you need to see this stuff. Um, but yeah, hold on. Let's erase all my drawings and just look at it again from the very beginning. All right, if our eyesight's looking here, because it gives us a reference point. BR is at the bottom. All right, we're looking at it. BR is at the bottom right here. We're just basically rotating this structure 90 degrees and looking straight down the barrel. Okay, straight down the barrel. All right, this left arm, because again, relative to here, this is our right, this is our left. CH3 is on this wedged arm, and H is on the dashed arm. And it's perfectly okay to just label them through their wedged and dashes. All right, well, we know from this, CH3 and BR must be on that same initial plane. And then CH, or I'm just going to call this our T-butyl group. Our T-butyl group is on the same plane as that CH3 group. So they're on the same side of the wedge. So the way we're looking at this right here, that looking down the barrel over here, what this image is looking at is basically from the side. And looking down the barrel is what we're doing to draw that Newman projection. Okay. Now the thing is, all right, well, wait, hold on. I don't want to move too fast. Does that somewhat make sense for everyone? It might make do to wait till the Fisher structures are shown, but do you guys follow on how I drew that still?
Yeah, it makes sense.
Yeah, I think.
Okay, cool. Great. Is go over it. These central carbons are our carbons like right here. This is supposed to be like into the page. Yeah. For drawing Fisher structures, well, if you remember Fisher structures, these horizontal lines are always wedges, right? Pretend those are neat wedges, and then these vertical lines are always dashes, so they're out of the plane. Well, we can use that to our advantage. Hold on, I'm gonna burp. Excuse me. What we do is we just rotate it. All right, if our two heads are CH3 and that T-butyl group, well, for me, I just rotate it. All right, well, this back ring, this is our bottom. And then for this front ring, this is our bottom. So we just rotate it so that they are eclipsed, basically. So if they're eclipsed, this is what our structure would look like. Well, CH3, 3, CH3, and then 8. Then our front ring, let's have them eclipsed. There we go. CH3, H, and then BR. So I would rotate your screen. I don't know why he drew it like this, but it's okay. I would rotate your screen so that, you know, this is at our bottom. So if this is our bottom, excuse my voice crack, and this is our top view, well, if these are already dashed, these are wedges because they're out of the plane. And whatever you have right here, you just slap them on this side. So Newman projection, all right, CH3 side, BR, H. That's from this side. Maybe I should make all this black and then show. I have an idea. Let's make that black. These are wedges. And these are dashes in the Fisher structure. These groups are wedges, and then whatever heads we have are our dashes. And then again, whatever we have over here, stage 3 and H, we just slap on this side, all right? Because they're in the same plane, they match up. So, let me erase this. Okay, that's whatever. CH3, H, and then CH3. Is that making sense for you guys? And how I did that?
A bit.
Yeah. Well, I don't erase that. Is it? Three. Yeah. What I essentially did is that I rotated this so that it lines up here, eclipsed. And when I did that, nope, not that one, this one, so it was eclipsed. When it did, H would eclipse with CH3 and BR would eclipse with that H. And whatever they're eclipsed with, they're on that same side of a specific Fisher structure. If we use this, if we use these structures for our E2 reactions, what you have to know is that it has to be antiperiplanar. So no matter what, for this back ring, okay, if our BR, our leaving group, is on the front ring, one of these have to be H's, because again, it's a beta hydrogen, but it has to be in the one very opposite to it. So for you to do that, let's redraw this, draw the conformation of the haloalkane for the elimination reaction using a small strong base. Well, for this back ring right here, there's only one H, so we just rotate it 120 degrees. H, this CH3 would rotate over here, CH3, C, CH3, 3. And then we have H, CH3, that didn't move. Once we line it up, we just eliminate these because that's our reaction to the small strong base. It swoops in, takes that hydrogen, and then it forms a double bond, or these electrons go here and form that double bond. But when you're trying to draw the structure of the alkene, what I like doing is, okay, once these are out of the picture, all I do is just butterfly invert it. So hold on, this is what I mean. So our C's are right here. We know we get an alkene. Well, I just move this down, move this up, and keep it on that right side. H down here, C, CH3 up there. Again, butterfly invert. Keeping it on that same side, CH3 move down, CH3 move up. They're the same thing, but it's, you guys get the point. Like this. And this is what we would see. Now our priority group is here and our priority group is here. So it's trans E. Do you guys get that?
Not really. Can you explain that again?
Sure. All right.
All I heard was something about butterflies.
Yeah, I'll go sort. You know what? Let's try throwing a different structure. So ignore this top part for now. Let's just have a plain E2 reaction. Yeah, just a plain E2 reaction. So for our initial Hayworth structure, ER, and let's just make these H's. Let's make it super simple. This would be H. This would be like, let's do, I'm trying to think of a really good one. Ooh, let's do an OH. Ooh, and let's do an NH3. There we go. It's very deactivated with those groups, but let's just ignore that for now, just for simplicity's sake. Well, okay, this BR has to be eliminated along with an H, and the H has to obviously be on a beta carbon. So the beta carbon groups are the ones in the back. Well, looking at the ones in the back, there's only one H. If there's no H, there's no reaction, and you have to look at a different perspective. But he won't throw that at you. So if this H is what we want, we have to rotate it so that it's anti-periplanar. So if we rotate it, well, we don't want to move the front ring too. Let's just keep it as it is because it makes it a lot easier if we just keep one thing straight and just rotate the other so that we can line it up. All right, don't move two things at once. If we just rotate that back ring, H is now over here, OH is on this side, and then NH3 is over here. Hold on, that's not a stereocenter. They have to be stereocenters. I know I just threw this at you. I'm so sorry. We have to make them all different or else they won't be stereocenters. God, I'm so shoot. All right, still the same thing. All right, NH3, we keep this front ring the same. Are you guys following on that? Front ring, I kept the same. I rotate this back ring so that the H lines up at the very top. OH would rotate down here. CH3 would rotate over there. And let's say we have our E2 reaction. All right, let's just, for simplicity's sake, a small strong base. And maybe let's solvate in DMSO. All right, well, if we have an E2 reaction, it's an elimination reaction. Our leaving group leaves, our hydrogen is stolen by that small strong base, and there's an alkene formed. There's a double bond formed. Well, when we're drawing our double bond, we already know, all right, we have an alkene, carbon-carbon double bond. This is all we have to do for our template. Now we just have to fill in the blanks. All right, so let's just recap. You know that, all right, you lined up our Br and our H, and we know that they leave. And we know that we have an alkene at the very end. So we just have to draw that and then draw the 4 branches coming out of it. Well, how do we draw our 4 branches? Well, all we have to do is imagine this. If this was our alkene, just imaginary map here. Just move this down to that one, and then move this up to that one. CH3 and H3. And again, move this H that was originally on top, butterfly invert it down here. So we have an H. And then our OH, we just bring it up. OH. That's all we do. So we look at it at the very beginning. This is what I mean by the butterfly stuff. We just move shit around. Forms the little wings. Okay. Well, you see here, the stuff I have in pink right here that was originally at the bottom, we just slap them on the top side. We keep them on that right side, and we keep them on their left side, respectively. We just keep them in the same lane, but we just swap them. All right, CH3 moves up, and NH3 moves down. So everything we had at top in H and in NH3 staying on their own sides, we just plop them in that bottom side. And literally, you just leave it as it is. Once you flip them, invert them, just put them down there and put the things, I sound crazy, put the things back up. You just leave it be. This, perfectly acceptable. Just leave it be and let it be a Berg and Patrick problem, because this is right. If you're right, you're not wrong. Do you guys follow?
Yeah, that makes sense.
Okay, cool. Sweet. Alrighty. For E2, the next thing is, okay, we know it has to be anti-periplanar, but if we were to use a chair conformation, all right, well, for cyclohexanes, they have to be anti-periplanar. So they have to be axial. So right here, as it is, our small strong base cannot swoop in and take that hydrogen. It's equatorial. It has to chair flip. I don't know why I'm doing that. Chair flip. There we go. I know you guys can applaud me for my amazing artistic skills. Don't worry. H, 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 Cl. Now these are axial to each other. Now that small strong base can come in and swoop that hydrogen away, form that double bond, and those electrons can now go to that Cl. And that's why it's super important. If you guys saw on your problem sets that I graded at like 2 a.m. last night because I was packing. So sorry if a notification woke you up. HCH3, HCl, H. It has to be on the opposite plane. Cl, if that's dashed, the one that has to leave has to be a beta hydrogen that is wedged on the opposite plane. Because right here, if this is equatorial, well, this same plane hydrogen would be axial. That means this opposite branch would be equatorial. Well, both of these are equatorial and we do this chair flip, they're axial to each other. What this is basically explaining, all right, well, if that's not really clicking, just know if our leaving group is dashed, then the hydrogen that leaves must be on the opposite plane. It has to be wedged on either one of these beta carbons. This beta carbon does not have a dashed hydrogen. This one does. So there's only one way it can go. So that was pretty short. You guys follow with that?
Kinda, but I have a question. Can you
Sure.
go back to the first Newman projection and like explain how you went from that to the Fisher? Because I'm still a little confused.
No. All right. Sorry, I keep feeling like I'm gonna say stuff that confuse you guys more. Trying to find the right way to describe it. Okay. Let's get black out of here. Let's just do a refresh of colors. Let's do purple. Let's keep that blue. All right. If this is what we're starting with, right? This Newman projection, we were able to build from that structure we were shown. And sometimes on a test, he might just give you the Newman projection straight up. All right. Well, if right here, this is our Fisher structure. And remember, this is a relative conformation. You can have any kind of group be in this bridgehead, and it can still be correct because there's different ways to write this. It's relative. That's why he has to give you some kind of branch already in place so that you know, all right, if this is where it is, and in our case, we have a T-butyl group at a head, and we have a methyl group at a head. There's only one way we can draw it now because we have, I'd say, starting points. All right, if this is our starting point, all right, from this, we can build it. So if our starting points are CH3 and our T-butyl group, well, let's identify that. Well, this is one carbon and this is one carbon. Those are our two carbons that we're looking down for this Newman projection. Because remember, Newman projections, we're just looking down two carbons. Well, let's identify our bridgeheads. That's CH3. On that back carbon, that's this carbon right here. And then we need one on the front carbon. That's this CH3 right here, right there. So these are, I almost said bridgeheads. These are the heads of our Fisher structures. Well, we know from test 2, all right, anything on a vertical line is dashed and they're away. So if we're looking at the Newman projections, well, let's pretend our eyesight was up here and we're looking down. All right, and this is what we're looking down right here. This is that top-down view already. We're looking down at this. Our T-butyl group and our methyl group are facing away from us. Well, let's just rotate this CH3. Let's just rotate this entire front carbon 60 degrees so that they're eclipsed. And if they're eclipsed, I know what I can do. No, never mind. There we go. Our CH3 group, CH3 group is over here. You can see we just rotated over. Rotate this 60 degrees and rotate this 60 degrees so that they're eclipsed. So we have our CH3, but on that back carbon, H, that's eclipsed. The H that was on that back carbon, and now that Br eclipsed. Let me make these blue. HBr. All right. Well, if we know that same plane, all right, let's pretend our eyesight was still looking down over here, looking down at this from that side. Well, let's do gray. These wedged carbons, or not the wedged carbons, but these wedged branches are facing toward us, all right? While these CH3s are facing away from us. That's why we want to keep that perspective. So if these are away from us right here, well, it matches our description and our Fisher structure. They're wet, they're dashed. So they're facing away from our plane. And you see right here, these are eclipsed and these are eclipsed. They're paired with each other. So they must be on the same side. So if that's the case, we just put them on one of these sides right here. And looking at this, all right, if our point of view is looking down here, then this is on our right side. This is on our left side. So the right side, HBr. And I know that because the Br is on that central carbon with the CH3. And then vice versa right here, CH3H. These are wedges. Let's keep it consistent. These are wedges and they're facing toward us. These are the same things that we're seeing over here. They're coming out of the page. This is the best I can explain it without a model set. If you're still confused, I can't help you anymore. Like, I don't know how else to describe this because this is really something that could be better explained in person.
No, that actually helps so much. Thank you.
Okay, cool. Sweet. The main thing is keeping it on the same side, knowing what's paired with what. With that, you're mostly there anyway. Now with this, we're going back to just having more practice with those butterfly inversion kind of deals. All right. So with these bonds right here, okay, let's draw a Newman projection with this right here. All right. Well, if we're looking down the barrel right here, CH3 is down, H is facing up. So we know that these two are already drawn or already there in our plane of sight. Now, on our left side right here, we have wedged and wedged. Again, if they're wedged, when they're on the same plane, they're usually going to be paired with each other. So we're going to have CH3, CH2, CH3. And then on our dash side, we just have H's still on our right side. Okay. And if we're looking right here, all right, well, in both of the, or in any case, Cl is our leaving group. So whatever hydrogen must be anti-paired planar from it. So it must be in this position. And we have two possible candidates of hydrogens. This first one that's already in position to be swooped down and taken, and another one that could be rotated and be taken instead. All right. So if that were the case, well, let's draw a second one if we were to rotate that backside. So leaving the front the same, let's just rotate the backside, H over here. That original H rotates 60 degrees over here. And this alpha group rotates 60 degrees, not 60, 120 degrees. CH2, CH3. These are plausible Newman projections. Because right here we have, all right, valid, nope, valid beta hydrogens that can be anti-periplanar to chlorine, which is our leaving group. Well, in our E2 reaction, these would be swooped down and taken. So they're out of the picture. Just ignore them. Now we have to draw our alkenes. Remember, our alkenes must obviously be a carbon-carbon double bond. So the structure looks something like this. And if we were to draw it like this, like our groups, well, these bottom groups, just flip them up to this top side. Here, let me draw like this. Top side right here over whatever groups we have. Top side. Top side. CH2, CH3, H. As you can see, the ones I circled, they were at the bottom, but now they're on the top side of that alkene. It's the easiest way to just draw it and keep them on the side. If H is still on that right side, just keep it on that right side. Just put it on that top position. And then you do the same thing with these top ones. Bring that H down, bring this CH3 down. So we get CH3, another H. Easy as pie. Once you draw that, leave it as it is. Don't mess with the structure. And for this one classified as E or Z, well, alpha, alpha. These always take priority over hydrogen. This is cis or Z. Then over here. All right, well, we bring this bottom one up here and we bring this bottom one up here. CH2, CH3. We bring this top one, still same left side, and just bring them down. CH3, then H. And now these are trans to each other. E. Does that make sense? How we got there?
Yeah, that makes sense.
Yep.
Cool. All right, now we have our oh so lovable synthesis. I love synthesis. A lot of people hate it, rightfully so, because if you can't figure it out, well, that's kind of booty cheeks, and I'm sorry. But if I always save this for last, in all honesty, because you can lose a bunch of time trying to figure it out, which could be used in answering other problems. That's why it normally is listed last or done last in the test. Is usually the last page if you ever do it in person. But if for some reason it's not, it's probably going to be one of your written portions. Save it for last. Right here we have a 2-bromopentane. And then we have a pentanal, just an aldehyde. How do we get from a bromine to an aldehyde? Well, we have, excuse me, we have to have multiple steps. The first thing is looking at the carbons. That's what I always do just to make sure. All right, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. They all have 5 carbons, so I'm not making any carbon bonds. I'm not adding any carbons. So we can stick to our just normal reactions where we, add an H and OH over an alkene, make alkenes, the stuff that we've been learning pretty much the last two weeks or so. Well, if our final target molecule is an aldehyde, what's the one reaction we know that can make an aldehyde? Right now, there's only one we know of. You remember that's
like BH3 and like
yeah,
the THF.
BH3, THF, H2O, H2O2, and H2SO4, I think. No, NaOH, my bad, has to be base, my bad. And in order to get there, we have CH3, CH2, CH2.
It's a double bond though, so isn't it a different one
What?
for the reaction going and creating the product, it wouldn't be that, right? Or am I
It would
just
be.
missing?
We can make an alkene or an alkyne from Br. You'll see in a little bit, but from what we have right now, the only way to make an aldehyde is through the bromination of an alkyne. It's the only way we know it. All right. Well, how do we get from a 2-bromopentane to an alkyne? Not that easy, but once you get the hang of it, there's only one real way to make an alkyne. So that's the beauty of semester 1 for synthesis. A bunch of the stuff they show you, there's pretty much one main way to make an alkyne, one main way to make a ketone, one main way to create an aldehyde, at least for test 3. Test 3. I think you learn one more way for each this coming week. But anyway, test 3, there's only one way to make for both. You can make an alkyne by an SN2 reaction with NaCCH and whatever like leaving group you have. Let's do like HBr and like another H. Backside attack leaving group. That's primary. You have a weak base SN2 reaction. However, that adds carbons. It adds carbon-carbon bonds. So that's not what we're going to be doing. So if that's the case, well, and we need an alkyne, the only way we can do that is with our freakishly small, strong base. And this is a super important reaction. If you haven't written this down from the notes, please write this down, because I can almost guarantee you, of all the practice tests I've seen for all the great synthesis problems, these come up pretty often. NaNH2, NH3. Very important reaction, because we can create an alkyne from this. How do you create an alkyne? Well, CH3, CH2, CH2, Br, Br. If you have a vicinal halogen kind of deal, well, your freakishly small strong base will just basically eliminate these and eliminate the hydrogens, or eliminate the hydrogen and create that triple bond.
Did we drop a carbon?
Hmm?
There were 5 carbons in
Oh,
the.
my bad. Yeah.
Okay, I was just like, is there an equation I missed?
There we go. So that's how we get an alkyne, just basically dropping the 2 Brs and then smack 2 pi bonds on it. That's something super important that you should know. Now we can work with it. All right, how do I get from a bromopentane to a double bromopentane? Well, there's no one reaction, unfortunately. You can't just HBr this stuff. There's no alkene. However, there is a way we can get a dibromo. How can we get a dibromo? Someone wants to throw it out. It's one of your test 2 reactions. Whoa, someone said it. I think I did. It's here. Bromination, Br2, and then some polar aprotic group. Double bromination. How do we get there? Well, remember, if you have an alkene and you react with Br2, we just add those 2 Brs. And hopefully you guys can see I was doing this all backwards, because personally, backwards is the best way to do it, because you can figure it out, because there's kind of a tunneling kind of deal. If you start at the very beginning, there's many different ways to do it, but if you start from the very end, well, some things can be crossed out if you go backwards, right? You're following your breadcrumbs, basically. So right here we have an alkene. All right, alkene going to a dibromo. And now we can have a reaction going from that bromopentane into that that pentene. And what reaction is that? I'll give you guys a hint. Bromine right here is secondary. Excuse me. Someone please throw it out. Okay, good job. Large strong base. Small strong base also works, but that's not the elimination we want because this is a Hoffman product. Because right here we have a primary, another secondary. If we want our Hoffman product alkene, we have to use a large strong base. So what's the only large strong base we know? This butoxide. There we go. Yeah, that's it. That's our alkene. Alkene to a dibromo to an alkyne to an aldehyde. Now we're starting from an alkyne going into a terminal alcohol. Well, let's look at our carbons. 1, 2, 3, 4. 1, 2, 3, 4. We're not making any carbon-carbon bonds. We're just adding an OH. Well, let's go ahead and draw our arrows. We have to start somewhere, and then we have to end somewhere right here. If we're looking at this, well, at the very beginning, we can't really do much. Because for an alkyne, you can do like Lindlar's, lithium or sodium ammonia. You can make an aldehyde, make it a ketone. There's a lot of different things you can do. But for an alcohol, right now, from the content we've learned, there's not many reactions relatively that make alcohols, especially terminal ones. Because we're making a terminal alcohol, all right? Well, let's look at our alcohol additions. We have H2SO4, H2O. We also have our bromination, not bromination, boration, BH3, THF, H2O, and AOH, and H2O2. Which one do you think we'll use? Which reaction? I'll give you a hint. This is, again, terminal. It's primary. Hello?
Sorry, Patrick. I literally have no idea.
It's all good. Synthesis, yeah, it's pretty little toughy. It's going to be our bromination. Oh, it's two. Because if our reaction is an alkene, because remember, the only way we can get an alcohol at this point is adding an H and an OH across an alkene. So if our alkene is something like this, then we want that terminal one to have that carbocation, or not for the boration reaction. There's no carbocation intermediate, but that OH still adds terminally. Now, how do we get from an alkyne into this alkene? It's a little tough. So let's just draw an arrow right here. Hopefully, this part you can't really tell straight up. This just has to be some thinking. Well, how do we create an alkene? Well, we can create an alkene through Lindlar's catalyst or lithium ammonia or sodium ammonia on an alkyne. However, if that were the case, our alkyne would have to look something like this, which is what we don't have. Another deal would be is if we had an elimination reaction. An elimination reaction creates a double bond. That's pretty great. So our elimination reaction would have to be something like this, Br, or something like this, Br. Because obviously we can easily make something like this, because that's just any small strong, or it's primary, so it has to be a large strong base. For secondary Hoffman product, still large strong base. So either one of these is acceptable. Now let's try getting from an alkyne to one of these bromobutanes. Personally, I think it might be easier to just add that bromo or that bottom bromobutane, because what if we had an alkyne like this? That's just adding an HBr over it. Now we're getting somewhere. How can we get, now this is something I will need you guys to answer. How do we get from an alkyne to an alkene? There's two reactions, possible reactions. Actually, no, three. There's three possible reactions.
Linlar.
Yep. Lindlar's catalyst. Any of them are acceptable because right now, since we're adding HBr and we're reducing that alkyne down to a sigma bond, regioselectivity is not a problem. So you can do any one of the reactions. The first one, let's just call it A, Lindlar's catalyst, H2, Lindlar's. B, another way you can do it, H2, lithium or sodium, ammonia, and like 0 degrees or something very cold. I forgot which one. And then just H2 PDC. And I don't know, like not in excess. Because if we did 2 parts of H2 PDC, it'll reduce the entire thing into an alkane. But now that we have this, all right, well, let's run through it. Let's just do Lindlar's. Alkyne, we use Lindlar's catalyst, we create an alkene. If we have an alkene, we have a but2-ene. We can add HBr and make an internal bromobutane. That internal bromobutane, if we react it with a large strong base like butoxide, there we go. Then we can create a Hoffman product of an alkane or alkene. And with that Hoffman product, we can just brominate it, not brominate. I keep saying brominate, borate it, make a terminal alcohol. Synthesis problems are kind of tough. Yeah. Yeah. That's all I have for it. Yeah. I would say the great synthesis problems that he posted are perfect practice, because he will have, for most of the tests you guys have for, well, semester 2, he'll have synthesis questions, and he usually posts great synthesis problems regarding that. And personally, on top of grinding out the practice test he gave us, I grinded out basically all of those problems, and yeah, I did pretty well. I'm not saying that will happen, but like the practice in itself, pretty much those patterns I saw, those I used on the test, because I just built them up. Because literally, they train your mind. What, I just exited out of it. They train your mind to have good habits on certain things. Don't look at that. Don't look at that. Where was I? This one. They train your mind to basically just have certain moves in mind. For example, aldehyde. All right. The only way you can make an aldehyde is through an alkyne. And an alkyne can only be made through Na, NH3, NH3. That's supposed to be 2, my bad. That's a very common move. So if your target molecule is a ketone and aldehyde, you already know half the reaction. We just have to create an alkyne with our freakishly small, strong base. Another move, Lindlar's, we have an alkyne. Oops. Hold on. Let me try to think of something really good. If we have something like this, an internal butene, and we're trying to make a terminal butene, how can we do that? We can't just flip that side over there. Well, right here, okay. make an alkene, we can do an elimination reaction. So that could be like something like this, Br, and then a large strong base. And then right here, we can just do our HBr. Alkenes in general can be made here. Let me keep that there. Another way an alkene can be made is with Lindlar's catalyst. That's the one I like, Lindlar's H2 from an alkyne. An alkyne can be made through, again, NaNH2, NH3, and from something like this, Br, Br. That's something really tough. Yeah, that is really tough. Ignore that one for now. I don't know where I was going with that. But Lindlar's and then large strong bases are ways you can make alkenes. But knowing certain pathways that tunnel into a specific functional group are super helpful. And you can pretty much figure all of that out by doing the great synthesis problems. So if you still haven't done, your test is tomorrow. So I would highly suggest you guys work on that tonight. But if that's the case, does anyone have any last minute questions? Because I'm probably going to run through this like really quickly. No, or not really quickly, but like just run through it. And then that's probably going to be the end of it. Does anyone have any last minute questions on this kind of stuff? I'm going to take that silence as a yes, and I'm going to go ahead and run through this. Oh, okay. All right, where's my Zoom? Where's my Zoom button? Okay, I'm still recording. Good. All right, well, now let's just run through this. If you guys saw the video, that's great, but I'm going to be running through the same thing. So when I look at a chart like this, and I'm pretty sure he's going to give you guys a chart, just identifying what we're looking at. So the top row, just identify it, all right? Nucleophile equals solvent at high temperature. So we're looking at E1 situations. And SN1, if it's benzylic or allylic, because there's no double bond that can be formed. But it's mostly going to be E1. Let's see C3OH over here. Again, nucleophile equals solvent, and that's going to be SN1 reactions. Right here, we have a weak base, and weak bases can only do SN2 reactions. A large strong base, we're going to see an E2 reaction, unless, again, it's like methyl or something. And then we have a small strong base, which is, again, mostly going to be E2 reactions. We might see an SN2. But from this straight up, we can pretty much build a bunch of things, but I'm getting a little ahead of myself. Let's just label this left side now. 0, because that's methyl. This is tertiary. Primary. This is primary, but don't forget it's allylic. And because it's allylic, carbocations, when that bromine leaves, are stabilized. So SN1 and E1s are perfectly feasible. This is secondary, not benzylic. Because if a carbocation was right here, it's still 1 carbon away from the benzene ring, and double bonds cannot conjugate over. So that's purely secondary. This is tertiary. This is tertiary and allylic. Now that we've identified it, let's go ahead and knock out the easy ones. So the easy ones are going to be our SN1, SN2, and E1 reactions. So for SN2, or for weak bases, they can only do SN2, and weak bases cannot react with tertiary. So it's really easy to just work our way down. All right, methyl group, SN2. Tertiary, no reaction. Oh, hold up. No reaction. Primary, SN2. Primary, SN2. Secondary, SN2. Tertiary, no reaction and no reaction. That's already 20%. That's pretty good. Now let's work on our nucleophiles equal solvent. I'm going to go back. All right. Well, if we're looking at our cold temperatures, remember, cold temperatures are very correlated with SN1 reactions, and they can only react with stabilized carbocations or tertiary compounds. So already, let's just go ahead. Methyl, no reaction. Primary, no reaction. Primary allylic, possibly. Hence, it is possible we're getting SN1. But the main thing is looking at the non-tertiary ones. Secondary, no reaction. Taking it back from the top, all right, tertiary, SN1. Tertiary, SN1. Tertiary, SN1. And the fact that it's allylic makes it, in real life, makes it faster, but it's still SN1. Boom, already 40%. E1. All right, E1, same kind of deal, all right? No reaction for anything that's methyl, primary, secondary, assuming it's not allylic or benzylic, or basically stabilized by double bonds. So there's no reaction. That's tertiary. Primary, no reaction. Primary but allylic, we'll get a reaction, but we'll get to that later. Secondary, not benzylic, no reaction. Now let's just take it back from the top again. Tertiary, E1, easy. Allylic, but it's primary, E1, stabilized. Tertiary and tertiary, E1. Already 60% of your chart can be knocked out just from your knowledge, because again, weak bases can only do SN2 and only on methyl, secondary, primary. And then it's mutually exclusive for our SN2, SN1 and E1 reactions. The hard ones are the small strong bases and large strong bases that you have to memorize. Large strong bases are pretty much going to be Hoffman E2, but let's look at our small strong bases. Well, methyl groups can only do SN2 reactions because there's no other carbon to make a double bond with. So even if it's with a large strong base or small strong base, we're going to get SN2. Small strong base with a tertiary, we're going to get an E2. And there is regional selectivity. We have primary, secondary, beta carbons, and we're going to do Zaitsev because it's small strong base. All right. And for here, there must be Hoffman, E2, Hoffman. Primary, all right, SN2, E2. Neither Hoffman nor Zaitsev, because there's only one part where that double bond can form. So there's no, it's neither Hoffman nor Zaitsev. All right, allylic is primary, SN2. Normally. This one, it would be, I think SN2. I think on the key, if you're looking at the key, it says SN1. I think that I'm pretty sure that's wrong. It's SN2 because it cannot create a double bond right there because that's already an sp3 carbon. Secondary, all right. E2, Zaitsev. E2, Hoffman. Same thing with this tertiary, E2, Zaitsev, E2, Hoffman. For this one, even though it's tertiary, there's only one way it can go on one of the, which is one of these methyl groups. It doesn't really matter which one because it's not a stereocenter. Two of these groups are identical, but it cannot go to the secondary one because that's sp3 hybridized. It cannot have another double bond. This is just plain E2, and this is plain E2. And that's our chart. Don't forget, whatever leaving group we have has to be on an sp3 carbon. If it's on sp2, there's going to be no reaction. Make sure you guys take a look at the charts I posted. Maybe I'll probably post the cohesive chart at the very end. But does anyone have any questions regarding this chart? All right. If there are no further questions, I'll stick around for a few minutes, but that's going to be the end of the review session. We completed everything we needed to. This is probably the last time I'm going to record something because I will be out of town next week. I'm actually about to go home and get ready for my flight. I already packed and everything, but yeah, that's going to be it. For those of you watching the recording, good luck on your test. It was a big pleasure being able to work with you guys. It's actually a lot more fun. It's a big step outside of normal Gen Chem because some people in my fall semester might remember me because I was their Gen Chem TA, but it's just a lot of fun. But I'm gonna stop my share. You guys are welcome to head out and stick around for questions if you have any.
Thanks, Patrick.
Of course.